Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my great pleasure to welcome Jeff Ullman to Microsoft Research. I don't think Jeff really needs an introduction, but I'll indulge in it for a few minutes. Jeff was the Stanford Usherman, I'm sure I'm mispronouncing it, Usherman Professor of Engineering at Stanford University. Since then, he has retired. He was elected to the National Academy of Engineering in 1989 and American Academy of Arts and Sciences in 2012. He has many awards. I'll just mention a few. He was awarded the 2010 IEEE von Neumann Medal along with John Hopcroft. He's the winner of the ACM SIGMOD in the Closer to the Database Field Contributions Award, Innovation Award, Test of Time Award, and then, well outside of that, in the Knuth Prize, Karlstrom Outstanding Educator Award, and so these are some of the most significant awards in our fields. He's an author and co-author of 19 books. I doubt any one of us have made it here without reading one of his textbooks. He has a latest textbook which sort of focuses on data mining, data parallel systems, and data integration. You can download it if you want. There is more information that is in the Wikipedia as well as in his webpage. Jeff also is my advisor, and he taught me how to do research. And he has some of the very well-known database folks who have been his students, such as Dave Meyer, who has visited here several times, Mihalis Yannakakis, and Jeff Norton, Anand Rajaraman, and you'll know many of them as well. I'll just say two interesting stories about Jeff. One was not my story. It was told to me by Jeff Norton. And Jeff Norton said, so he was doing his thesis, and he was wrapping up the thesis, and then he would give Jeff a copy, and Jeff would mark it up with changes and give it back to Jeff Norton. And this process was continuous, going on for a while, and it was not clear how you break the loop. And then somebody said, just instead of giving him with the thesis, just present him with the one to sign, the page in the thesis that you have to sign, and then the thesis was done. So I can't say these jokes as well as Jeff Norton does, who is an outsider.
Get a laugh.
Yeah. and the last one was this is really stunned me when I was in the NAIL group with Jeff, and there used to be very intellectually intimidating moments with Shuki Stagiv, used to be from Israel, would visit, and then Moshe was at IBM Almaden at that time. But in addition to that, there was a very interesting case that one of Jeff's ex-students, who had graduated, was at IBM Research, and he has visited, and he says he was talking about a problem, which I don't remember anymore. And he said that I'm really trying, it's an NP hard, but I don't have quite the proof. In a few minutes, Jeff actually had a polynomial time construction of that, showing why it was so hard. So with that, Jeff, take it away.
Well, thank you for that introduction. Okay, so anyway, you can try to see an outline of what I want to talk about. Okay, we started off as a sort of a theory of MapReduce. It actually applies to the more modern workflow systems, but only as far as the algorithm going from one stage to the next stage. Unfortunately, except in one small exception involving matrix multiplication, we really can't say anything for multi-stage algorithms yet, and I'm hoping that maybe somebody will think about that. I then want to talk about sort of the problem that got us really going on this theory of involving some students at Stanford who managed to basically write an algorithm, a MapReduce algorithm that didn't work, and how we fixed it. Then I want to introduce the theory itself, which we think of as what we call reducer size versus replication rate. It's really degree of parallelism versus communication. And then I want to go through a couple of problems for which we have analyzed the best possible algorithm. Okay. These are people who have helped in the various, in one or more of the various sections that I'm going to talk about. I want to thank them all. Okay, so the idea is MapReduce is not a completely general parallel programming system. And there are some, it gives you some fairly subtle limitations. And what we want to do is develop a theory that sort of explains what the limitations are and enables you to design algorithms that meet the constraints. So I want to just start off by going through MapReduce. In case somebody has been living under a rock for the past 10 years and doesn't know this, I just want to introduce at least my terminology for this. Okay, so we're going to talk about a MapReduce job. You have a collection of inputs. The inputs are all of some type, arbitrary though. The user writes a map function, and that map function is applied in parallel and independently to each of the inputs. And so I want to, this is perhaps a little bit non-standard, but I want to refer to a mapper is the application of the map function to a single input. Okay, you may be more familiar with the notion of a map task, which is sort of the unit of parallelism. That's the application of the map function to some large number of inputs done serially. Okay, but in principle, the map, because the application to every input is independent, you could do them all in parallel if you had enough resources. Okay, then the map function produces a set of key value pairs. What's only really important is just that it produces some amount of data that's sent to the next stage, which is the reduce stage. Behind the scenes, the system sorts key value pairs by key, and what is passed to the next stage is the key and a list of all the values associated with that key. And then there's another function that the user writes called the reduce function, and it's applied to a single key and the list of all the associated values. And again, I want to use the term reducer to mean, again, just the application of the reduce function to a single key and its values. And again, the unit of parallelism is a reduce task, and usually many reducers are executed serially as part of one reduce task. But that's, again, not important to the theory. And then the output is the union of what each reducer produces. So you have this sort of two-stage or two ranks of parallel processes picture. Inputs go into the first stage, the mappers. They feed in possibly all combinations, as I've shown here, more likely some small subset. Each mapper feeds a small subset of the reducers. But in principle, reducers can get their input from anywhere, and the output is the union of what the reducers produce. Okay, so obviously you're going to pay for the execution time, total time to execute the mappers and the reducers, and there's a communication cost of transmitting the output of the mappers to the reducers. I'm going to assume that even if you not executing every mapper in parallel at the same time, you have enough compute nodes involved that the chances that the output of a mapper will go to a reducer that resides at the same compute node is very small, and so I'll assume it's 0, and just count the cost of moving any mapper output to its reducer input as a unit cost. And then there are many examples where the communication cost is in fact your bottleneck, and so I'm going to. It was certainly true in the example, which I'm going to get to next, but it appears to be true in many cases. Okay, let me comment. People are getting off of MapReduce or Hadoop these days. There are a number of workflow systems. They're sort of multi-stage, acyclic systems. Like the Dryad was probably one of the first that was developed here. Now, of course, probably everybody's heard of Spark. All of these systems have the same characteristic that they have. There will be, instead of 2 stages as with MapReduce, you have many stages, each stage feeding stages up the line. But again, I wish the theory would apply to the to these more general systems. It does apply to to what goes on between one stage and the next stage. Again, I wish we could generalize that, but at least you can't. The theory doesn't go away just because people are no longer actually using MapReduce. Oh, I could talk about that at length. I'm not going to do that. I'm happy to talk about it offline. But there's intuitively even in 3 stages, there's too much mixing of inputs to outputs. The thing that makes the theory go is the fact that not every input can feed every reducer or second rank guy. And once you have a third rank, things just tend to get too mixed up to get anything strong. Anyway, so the essence of what's going on, if you don't like MapReduce, the only thing you need is that the first rank produces outputs based the outputs depend only on one input, and then that the outputs depend only on one process at the second rank, and the same theory will go through. Okay, so anyway, let me tell you sort of what got us started on this. Every spring we teach a course in data mining projects where the students have to propose their own project and they get a faculty coach. And Amazon has been providing AWS service to the class. And so I was coaching a team that had actually data from the Stanford Medical School. And this was his 20 years worth of patient data. They had extracted from that the records for 3,000 drugs, which is roughly half of the drugs that the FDA has approved. The 3,000, the only reason they didn't do the other 3,000 was because they were so rarely used that there wasn't enough interesting information about them. So they had organized this into a record for each of these 3,000 drugs. And it was about a megabyte long, and it contained the history of all the patients, anonymized patients, that had been given the drug and what had happened to them. And their goal was to find drugs that, when taken together, increase the risk of a heart attack. So they really what we're doing was for each pair of these megabyte-long records, they were going to do a chi-square test to see whether there was anything statistically significant about people who people were more likely to have a heart attack if they took both drugs than if they took only one of them. Okay. So there's a lot of computation. They're going to do a lot of parallelism. So this was, I guess, the first Hadoop algorithm that they'd written, and so they did something very simple. They said, we're going to use as keys, we will use, the keys will be sets of 2 drugs. And the values that we'll generate will be the record for one of these drugs. So again, the inputs are the drug records, and the mapper is going to take that drug record and just, well, the mapper for the drug I takes the record, generates all the key value pairs of the form ij, where j is a drug other than I, and attaches as a value the record for drug I. Now, from the point of view of the reducers, the reducer for the set ij, it's going to get 2 messages. One from record, the mapper for I, one from the mapper of j, and it'll contain those 2 records. And it just do the chi-square test on those two records. So here's a picture of it. Now I didn't have space for 3,000 drugs, so I only did 3 drugs. So the mapper for drug 1, it'll produce the key 1, 2, because 2 is one of the drugs besides 1. And attach to that the drug 1 data. Do the same thing for the pair 1, 3. And the other 2 mappers do the same thing. Okay. And then behind the scenes, things magically get sorted, and then technically it's organized as a key and the list of values. And so now, for example, the reducer for this pair 1, 2 has the 2 records that it needs. It runs the chi-square test, and the output is the chi-squared value. Okay, so they did this. It was 24 hours before their midterm reports were due, and so I get an email saying, the thing isn't finishing. The AWS must be broken. Wait, I'm sorry. Wrong. Well, let's say there are 3,000 drugs. They generated 2,999 key value pairs per drug, and of course the bulk was in the value, which is about on average a megabyte. And you multiply that together, you get 9 terabytes. And it's communicated over typically gigabit Ethernet. I assume that's what was used. That's a little bit more than a day of network time. Now, of course, there's more than 1 gigabit Ethernet going on. But on the other hand, they're also competing with other jobs that are running on AWS at the same time. So anyway, bottom line was after 8 hours, they had not gotten a result, and they killed the job. So we sat down and we said, let's do something a little bit more sensible here. And I'm just rounding off the numbers. This was not exactly what they did, but it'll give you a picture. Okay, so you group the drugs into groups. There's 30 groups, okay, of 100 each. Now the keys will be pairs of group numbers, and the mapper that's given drug I in its record will now produce 29 key value pairs. The keys will be the group number for drug I and any one of the 29 other groups. Okay, and the value is essentially just the megabyte long record. We have to tag the drug number to that record so things don't get confused. And now, from the point of view of the reducers, the reducer for the pair of groups, say M and N, is going to get 200 drug records, 100 from each group. And it's going to have to compare each member of group M with each member of group N. So it's going to run 10,000 chi-square tests. Okay. Well, you also have to worry about 2 drugs that are in the same group, so they have to have some tie-breaking method. I forget exactly what they did. It's not important. Okay, at any rate, you're still just doing a chi-square test on every pair of records. You got 4.5 million pairs, but you're just doing 4.5 million chi-square tests. So the computation is pretty much the same. The computation at the reducers, in fact, is exactly the same. So the difference, of course, is the communication. Now, instead of 2,999 copies of everything, you were doing 29 times, about 100, a factor of 100 less. There's still significant communication involved, but it was enough for that they were able to get done in an hour and handed in the report a little bit late, but okay. Okay, so what's the theory all about? Okay, as I said, well, there are a couple of concepts I want to. I'm sorry.
So, like, that's at first you're decreasing the amount of parallelism for the reducer, aren't you?
Yes, right. But they didn't have 4.5 million virtual machines anyway, so they weren't really getting they weren't getting useful parallelism there in the original algorithm. And in fact, they actually, I think, only had about 10 groups, not 30. But even with 10 groups, you've got 45-way parallelism. So if you buy, 20 machines, you get all the parallelism you paid for anyway. So, but yeah, fair enough.
But is this fundamentally a query planning problem now? If I know how many parallelism I need, and then I can somehow come up with a plan that works?
Yes. Yeah, in the sense of you can pick the number of groups. Yeah, it's a little bit more subtle because, like I said, the records are megabyte long. They weren't all a megabyte long. You got some drugs like aspirin where it was probably 100 megabytes, and others that were 100,000 bytes and so on. You got skew to worry about, so exactly how much parallelism you very all sorts of complicated questions, but. If you just make sure that the number of reducers is like 3 times the number of machines you bought, you're probably okay. Okay. Anyway, so these are the cast of characters again. These the concepts of reducer size and replication rates. Mapping schemas are abstractions of MapReduce algorithms, and then I'll show you how to get lower bounds. That is, things that say you can't do things faster than such and such. Well, at any rate, okay. So the model is sort of embarrassing. This is not a profound model. It's really just many-to-many mappings. Okay, you have a set of inputs. In the example that I talked about, it's the drug records. That's each drug record is an input. You have a set of outputs. You can think of, in this case, the output is the chi-squared value for each pair of drugs. And then there's this many-to-many relationship that says which outputs depend upon which inputs. In the example, the output for a pair of drugs, I'll say I and J, depends only on the input I and the input J. And that's it. So here's a picture. In this case, for 4 drugs, you get 6 outputs, and they're connected in this kind of regular pattern. Matrix multiplication, another problem we'll talk about. This is not the full input-output mapping. It's the input-output mapping restricted to a single output, let's say in row I and column J. And the actual input-output mapping is the overlay of this picture for all of the n-squared pairs I and J. So it's got lots of connections, but it's a very regular pattern, and we're going to come back to this one. Okay, so the reducer size, which I'm always going to denote by a gold-faced Q. I'm glad to see it's visible here. It's the maximum number of inputs that I'm going to allow a reducer to have. Okay, so if we're actually talking about MapReduce as opposed to just 2 ranks of some more general system, it's the length of the value list. Now, for example, I might. Why do I care? Why do I want the reducer size to be small? Well, for example, I don't want one reducer to get more inputs than it can handle in main memory. because if it has to start shuffling things to disk, it's going to be that's going to be a problem. Or I might want my reducer size Q to be even lower, because the smaller Q is, the more reducers there are, and therefore the more parallelism you're going to get. Okay, the other parameter is the replication rate, and it's the average number of key value pairs created by the mappers. In all the examples I'll give you, all the mappers create the same number of key value pairs anyway. But anyway, we think it's just the average, and you can think of it as communication cost per input. Okay, so let's think about the drug interaction problem in general. Okay, so we have D drugs. D was 3,000 in the two examples, and then suppose I break them into G groups for some G. First time G was 3,000. There's one input per group, and then we went to 30 groups. G equals 30. Now, I can use the same idea. I hope that this will be obvious. That is, if the job of a reducer is going to be to compare the elements of two groups, so it has to have a Q that's at least big enough to accept the two groups, and that would be 2D over G. Okay. Now, if you remember, each input is going to get sent to G minus 1 reducers, those that correspond to its group and one of the other groups. Well, I like to just forget about plus ones and minus ones. So I'm going to just say that R is G. The number of groups and the replication rate are essentially the same. And now I can therefore replace G by R and get a relationship between Q and R. And I like to write it the other way around, because Q is essentially the thing you can control. That's the algorithm design. And R is a consequence. Okay, so we have R, in this case, this family of algorithms gives you a replication rate that's 2D over Q. Okay, so there's a trade-off. It says the bigger I make Q, the less replication I have, therefore the less communication cost. But also, of course, if Q is too big, then I get thrashing and very little parallelism. So there's a trade-off. I have to figure out what I want Q and R to be, but I can't just pick them both to be tiny. There's a lower limit on R. Well, I'm sorry, that's not clear. All we know now is that this is, if I use this family of algorithms, is an upper limit on R. Okay, and now I want to talk about, is that in fact the best we can do? Is that the smallest possible R? Okay, so the theory, again, I tend to think, I like to think of this as a theory that's analogous to the theory of sorting for sequential algorithms that was developed about 50 years ago, where people invented things like quicksort, which is an n-log-n sort, and then you want to know that you can't do any better. So you need a theorem that says, no, it takes time n-log-n to sort n items serially. So here I want to say there's a bound. I'd like to be able to say that the lower bound on R is in fact the R that you, as a function of Q, that's the same, that the lower bound is the same as the upper bound you get for that family of algorithms. Well, again, the concept of a mapping schema, it turns out to be important, and it's an abstraction of what a MapReduce algorithm is. Okay, in that it just says where do the inputs go. Never mind what computation is being done on them, but just which reducers get to see which inputs. Okay, so the first condition I want is that no reducer is assigned more than Q of the inputs. I mean, that's the definition of Q. But the more interesting thing is that you need to say for every output, there's some reducer that is associated with all the inputs that are needed for that output. Because, again, remember, every output has to be produced by one particular reducer, at least. And if that reducer doesn't see the inputs that are needed to compute the output, the algorithm is wrong. It's not going to work. Okay, so I'm going to say the reducer covers the output, and then, as I said, that if there's any output that isn't covered, this is not a mapping schema for this algorithm. Okay, so I claim that every MapReduce algorithm has a mapping schema that describes how it delivers its data from inputs to reducers. And I think that it's this existence of a mapping schema that really takes MapReduce algorithms out of the class of, well, they're just general algorithms, general parallel algorithms. Okay, so let's see how this works. Again, we're going to get a lower bound for the drug interactions. So again, I'm going to assume that there are D drugs. The reducer size is Q. Now, since every pair of drugs is an output, what that means is that each drug has to meet each of the D-1 other drugs at some reducer. Well, if I send a particular drug to a reducer, remember the reducer gets at most Q of the drugs, and therefore they are only Q-1 other drugs. So what this says is the number of reducers I need is at least the ceiling of D-1 over Q-1. Because the drug has to meet all the D-1 other drugs somewhere, and it can only meet them D-1 per reducer. Okay, so the replication rate is at least that for the ceiling. Essentially R is at least D over Q. Again, just throwing away the -1. Now you notice that's the algorithm that I described has R equal to or less than 2D over Q. So what's the difference? Well, it turns out that there's a better algorithm. I'm not going to talk about it, but you can get essentially down to D over Q. But using a much more complicated algorithm, one of these things that nobody would actually ever bother implementing.
Is that algorithm known before the analysis or published?
I doubt it. I certainly, I don't believe so. Okay, anyway, now I want to move on, talk about some other problems. The first one I want to talk about is HD1, or finding inputs of Hamming distance 1. And I assume most people are familiar with the idea of Hamming distance, but just remember, we have bit strings of length b, and the Hamming distance between two bit strings is the number of positions in which they differ. And the problem, I'm going to assume we're given all possible inputs of length b. That's silly. If I'm given all inputs of length b and I want to know which of them are at Hamming distance 1, well, that's no. I mean, just you don't actually have to compute anything. But what I'm really imagining is that only a subset of the inputs are actually present, and I want to find out among those that are present which are at Hamming distance 1. So what I'm going to really do, you'd really pick a Q that, let's say if a tenth of the inputs are there, you might pick Q to be 10 times what you'd really like it to be. Okay, let's say what you could tolerate if you wanted to do your work in main memory. Okay, so let's say b equals 2, probably the only number for which I can actually just show you do the example. There are 4 bit strings of length 2. Of the 4 choose 2 or 6 combinations, 4 of them are at Hamming distance 1. The one 0, 0 is obviously not Hamming distance 1 from 1, 1, and 0, 1 and 1, 0 are not an output either. So you've got 4 outputs, 4 inputs. Now there's a theorem, and I'm not going to prove it to you, but that R is both a lower bound and for many values of Q, let's say, also an upper bound, is it's B over log Q. Okay. See, so for the all pairs problem involving the drug interactions, the relationship was R was a constant divided by Q. Here it's R a constant divided by log Q. So it's a little different, but the same idea. The bigger the Q, the smaller the R. Okay, so let's talk about upper bounds. One thing you can do is you can have a reducer per output. And then, again, an output being a pair of strings at distance 1. So I'm going to send each input to the B reducers that correspond to the pair consisting of that input string and one of the B different strings that differ in 1 bit, that is, have Hamming distance 1. So that says you get a replication rate of B. And then, again, the reducer will just look at the pair. If both of them are actually sent to the reducer, then that says, yes, this is a pair at Hamming distance 1. And of course, this is not too chaotic, because if neither element, if neither input is actually present for an output, then the reducer actually doesn't exist if you look at how things are implemented. Well, at the other extreme is the serial algorithm. If Q is as big as 2 to the B, that's all the strings. Then we just send all the inputs to this one reducer, and we let it sort of do the serial algorithm. Okay, and then you have a replication rate of 1. So those are the two extremes. Now I'm going to give you one more algorithm. It's called splitting, and I'm going to assume that, just to make life simple, assume that B is even. I'm going to have 2 reducers associated with each string of length B over 2, that is half the length, and I'll call them the left and right reducers. And then I'll take any input W, bust it up into a first half and a second half, first half X and second half Y, and I'll send W to the left reducer associated with the half-length string X and the right reducer for Y. And now I want to make sure this algorithm works, so I have to say if W and Z are at Hamming distance 1, then they can't disagree in both the left half and the right half. And so if they disagree in the right half, then they'll wind up at the same left reducer, and if they disagree in the left half, they wind up the same right reducer. Okay, so it worked. So this gives you R equals 2, because again, every string gets sent to a left reducer and a right reducer. And Q is 2 to the power B over 2, because that's the maximum number of strings that have a given, say, left half or a given right half. So now I want to do get a lower bound, of course. Need to do that. And I think of it as 4 steps. The first one is actually the hard step in most cases. It says, I need to get an upper bound on how many outputs a reducer of size Q can cover. Okay. Then I can take the result of 1 and I'm going to take the number of outputs divided by that upper bound. That will give me a lower bound on how many reducers I need. Okay. Then I multiply by the number of reducers by Q, and that gives me the total amount of stuff that's going from the mappers to the reducers. And then I divide that by the number of inputs to get the replication rate which again is the average number of elements produced by each mapper. Okay. Now, I should remind you that if the upper bound grows at least linearly in Q, and in practice it always does, then I don't have to worry about something that might look like it's missing from this recipe, which is the could I do better if I had more reducers, but they didn't get their full complement Q of inputs? And as long as the first function is at least linear, that can never happen. Okay, so the way we prove that R is at least B over log Q, well, you need this lemma, which I'm not going to prove, that says if the reducer size is Q, then the number of outputs it can cover is this function here, Q over 2 times log Q. Yes?
So the previous slide basically gives you a recipe to get a complexity for your communication as long as you have a complexity for the serial algorithm, right? For the serial problem. Like, for example, this lemma of yours is basically the complexity of the non-parallel problem.
No.
It's like
No, it really has nothing to do with the serial algorithm. It just says.
No, lower bound for the serial problem.
Wait.
Like this lemma.
Are you talking about point 1?
Yeah.
Yeah.
The first.
Yeah. I mean. Again, it's just a combinatorical. It's a combinatoric question. It's not has nothing to do with any algorithm. It just says, I'm given some number of inputs, and how many of the outputs could possibly be covered by a set of Q inputs, and that, of course, it depends on what the input-to-output relationship is.
That's true.
But it doesn't depend. It has nothing to do with the algorithm itself.
No, you're right. It's just basically an upper bound, right? That's for the problem, not for any particular algorithm. But I'm just saying, like, pick any problem that you want, as long as you can basically give an answer to the bullet one. Then with your recipe, you can find a lower bound for the.
Yeah, that's right. I mean, the hard part is always getting that upper bound, and that's a function of the problem, not exactly of the algorithm, but of the particular problem.
Yeah, I guess like for matrix multiplication, you are going to use the same thing, the same lower bound that we know for offline or non-parallel matrix multiplication.
Well, yeah, probably, yeah. Okay. I think that's true. Okay. At any rate, okay. So you need this lemma again. I'm not going to go into it, but you divide the total number of outputs, which is b over 2 times 2 to the b. I'll let you figure out why that's the number. That's the number of pairs of strings of length b that are Hamming distance 1. Divided by this function, you get that, and then you multiply that by q. That just sort of knocks this over q out of the picture, and then there are 2 to the b inputs, so you divide, that knocks the 2 to the b out of the picture, and so you just get r is at least b over log q. Okay. So this is the lower bound, and the first algorithm I gave you that has a replication rate of b, one reducer for each output. The q, of course, is just 2, or 2 to the first power. So that's at that end. The serial algorithm is at the other end. The splitting algorithm is sort of in the middle. It's got a replication rate of 2 and a reducer size q to the 2 to the b over 2. And then there's a generalized splitting algorithm, which we're not going to talk about, that for any integer replication rate gives you an appropriate reducer size that lies exactly on the lower bound. Okay, so at least for an infinite number of values of q, there are a matching upper and lower Okay, I want to just talk about matrix multiplication a little bit. I guess in this case, I'm going to start off with the lower bound for one-round algorithms. I'm going to, well, the optimal one-round algorithm is I guess what you call the serial algorithm. Is the obvious thing. And then I'm going to just comment that 2 rounds are better than 1. So this is the only case where we're able to get something interesting that involves more than 1 round. And here it's using the lower bound for the 1-round algorithm, and then you just have to invent a 2-round algorithm that is in fact better.
So what do you know about the Hamming problem when the Hamming distance is more than 1?
Nothing. And although I was actually talking this morning with one of your interns who does know something about that, but not to the extent of having matching upper and lower bounds. So that's still somewhat open. Okay, so matrix multiplication. I assume everybody knows how that works. This is dense multiplication of square dense matrices. Okay, so the outputs, the inputs are going to be A on the left, B on the right, and C will be the result matrix. And then the output CIK obviously depends upon the entire row of the first matrix A and an entire column of the second matrix B. And remember, if a reducer is given anything less than a full row of A and a full row of B, then it can't compute that output. Okay, so what this sort of says is you might as well think about transmitting either whole row. You might as well either transmit a whole row of A or nothing, because part of a row just doesn't help. And likewise, either transmit a whole column of B or don't bother transmitting it at all. So again, there's just a picture of how you compute an output, of what you need to compute an output. Now, again, I want to going through that recipe. In order to get a lower bound on replication rate, I need to get an upper bound on what can a reducer that gets Q inputs do. Well, the first observation is, again, the best thing it can do is to get some number of rows of A and columns of B. And how many of those can it get in total? Only Q over N, because each row and column is of length N. So it gets at most Q over N rows and columns. And then it's just a little thought that says to get the maximum number of outputs from a reducer, you have to have the same number of rows of A as you have columns of B, because the square has more area than any rectangle of the same perimeter, roughly. Okay, and so that's the reducer is going to get at most Q squared over 4N outputs. I'm not going to go through all the math, but what it gives you R is at least 2N squared over Q. And so this is this inverse relationship again. And by the way, it's 4N to the 4th over Q is the total communication. Now, there is a matching algorithm, and each reducer, you divide the rows of A into G groups, you divide the columns of B into G groups, and one reducer gets that set of rows, a group of rows and a group of columns, and produces the square of outputs that's in its excuse me, that's in the intersection. I assume that's what you meant by the serial algorithm, right? Yeah. Okay, and that turns. Yeah, right. So yeah. So the obvious thing in this case, it does match the lower bound. On the other hand, I'm not going to go into it, but there is a 2-round matrix multiplication algorithm, which the total communication between the two, summing over the two rounds, total communication is 4N cubed over square root of Q. And that is in general going to be less than 4n⁴ over q, which is what the communication for the one-round method.
We have to keep q within the order of n, right? Because the total complexity of matrix manipulation is n cubed, right?
Well, no, q would have to be at least 2n, because if it's not 2n, you can't get a row and a column, you can't do anything.
Right.
Okay, but q could be, for example, n to the 3 halves.
Okay.
In which case you'd get the ratio of the communication is n to the 1/4.
Oh, q contains, okay, the number of rows multiplied by whatever number of columns you want to consider. Okay.
Okay, so the last thing I want to talk about is marginals. Just to introduce the story of marginals, I hope most people are familiar with the idea of a data cube. You can think of it, it's really a relation in which certain of the attributes of the relation are called dimension attributes, and these are sort of the independent variables. Often this is done to sort of tabulate sales of an organization. So you might have a dimension corresponding to items sold, dimension corresponding to the purchasers, dimension corresponding to the store where it is sold, dimension corresponding to the day on which it's sold, and so on. And then the points of the cube each represent a fact, and it lives, of course, in this dimension, this multi-dimensional space. So a point in the cube might represent a certain item purchased by a certain buyer at a certain store on a certain date. And then there will be the sort of payload. There are certain other attributes which are the things you want to sum over or aggregate over in some way, like the price or the quantity. Okay. And the interesting queries are often these marginals in which you sum over some but not all of the dimensions. So, for example, you might want to know for each store and date what is the total sale of all items to all purchasers. Okay, and again, so a margin. And the idea is you can pre-compute these if you like. So you can compute all the marginals, which are again the sum of one of the dependent attributes taken over all points in the data cube that have fixed values in certain of the dimension attributes, and you're summing over the other attributes. And I'm going to say marginal is kth order if you're summing over k of the dimensions and the marginal has fixed values. You're getting summing over only points with fixed values for the other attributes. Okay. Now, I'm going to make an assumption which is clearly not true, but makes the math a little bit easier, a lot easier. I'm going to assume that for each dimension there are exactly d distinct values. That is, there are as many customers as there are stores and so on. That's complete nonsense, of course. It does make the algorithm, the discussion, considerably simpler. And once we do the discussion, we're going to realize that d doesn't matter all that much because, in fact, the cost only varies logarithmically with d. Okay. Anyway, I want to talk about a MapReduce, single-round MapReduce algorithm to compute all the kth order marginals, again, in one round of MapReduce. Okay. So the first thing I'm going to do is I'm going to pick a reducer size which is d to the power m for some m which is at least k. Because if I pick m, if q is less than d to the k, then I'd never get enough information to compute, enough inputs to compute any marginal. So that's impossible. But typically I'll want m to be somewhat larger than k so I can compute lots of marginals at one reducer at the same time. Now I'm going to pick some sets of s dimensions, and For each set S, I will have a family of reducers. Okay, again, family, this is a key term here. The reducers now live in families, and the family has one reducer for each of the possible assignments of values to the dimensions that aren't in the set S that corresponds to that family. Okay, so you have lots and lots of reducers in a family. Now, I'm going to send each point of the data cube to exactly one member of each family. And it's going to be that member such that it agrees with the member of that family in the dimensions that are not the fixed dimension, the dimensions for which that the family has, the dimensions that are not in the set S, the n minus m fixed dimension. So as a result, the replication rate will be the number of sets S that I choose. So the interesting question becomes, how few sets S can I pick? And again, remember, what we're doing here is we want kth order marginals. I'm going to pretend that I want an mth order marginal, and I'll send to each reducer in the family all the inputs that I need to compute one mth order marginal. But in fact, what I'm really going to do is compute many kth order marginals. And it turns out, I'm going to state it, not prove it, but there's an interesting proof that says, given that you want reducers of size d to the m, this is the best way to do this. You get more marginals out of one reducer this way than you could with any other reducers of the same size. Okay, as I said, then the replication rate is the number of sets I choose, again, because every input sent to one reducer in the family for each of the sets that I choose. Now, I claim a family associated with the set S of dimensions can compute the marginals collectively. The family computes all the marginals that aggregate over sets T of size K, if and only if T is a subset of S. Okay, and well, the argument sort of is that if I want to compute the marginals of size T, I fix the m minus k dimensions that are in S but are not in T, and I can do that in all possible ways. And then each reducer in the family, of course, has fixed values for all the dimensions that are outside of S. There'll always be one reducer in the family. Given any assignment of values to the dimensions that are not in T, there'll be some reducer in the family that has all the data that it needs. That is those points of the data cube that have those fixed values and all the attributes other than T. Okay, so the problem then becomes, do we have to pick all possible sets of M? No. We want to pick as few sets as possible. Just to give you an example, suppose there are 5 dimensions. I'll call them A, B, C, D, E, and I have k equals 2 and m is 3. So I want to compute second order marginals. I want to cover sets of size 2 with sets of size 3 out of the 5 dimensions. One thing I could do, well, here's one possible solution. I'll let you figure out why all of the 10 pairs from A, B, C, D, E are contained in one of these 4 sets. And that's optimal because there are 10 pairs. A set of size 3 can only cover 3 pairs, and therefore I need at least 4. Because 3 triples can only cover 9 pairs. Okay, so this turns out to be a classic combinatorial problem. It's called covering numbers, and C of n, m, and k then is defined to be the smallest number of sets of size m, such that every set of k out of n elements is contained in one of the sets of size m. Okay, there's a lower bound. Interestingly, can be met for an infinite number of interesting cases, but most of the time it's something larger. C of n mk is at least n choose k divided by m choose k, because n choose k is the number of things that have to be covered, the number of sets of size k that have to be covered, and m choose k is the number of sets of size k that any one set of size m can cover. Okay, now I'm going to just state the theorem, and again you need this upper bound. We're always asking the question: if I have a reducer of size q, how many outputs, in this case marginals, can it cover? Okay, so the theorem says if I have an n-dimensional cube whose side is d, and I pick any q points within that cube, it turns out that the greatest number of subcubes of k dimensions that can be contained within this set of points is q divided by d to the k times log of q base d choose k. Now, never mind that this isn't even necessarily integer. What this really is a gamma function. Don't worry about it. But if q happens to be d to the m, then this formula, in fact, this really is a combinatorial value, and that's what it is. And if you think about it, again, I'll let you think about it. That is exactly how many subcubes of dimension k we cover with a reducer that shares fixed values in n minus m dimensions and all possible values in the other in the m dimensions. So that says the method we gave really is the best.
So this is basically picking the set T of size K and then checking all possible remaining dimensions, right? In the set S.
I'm sorry, maybe there's bad notation. Is this set S is just a set of points of the cube? There's nothing to do with the sets of dimensions.
I'm saying like the matching algorithm for this lower bound on the rate that you
is the one that we well, I'm sorry, it's not exactly an algorithm. What it says is, if you're given q, it says the best thing you can do is to pick.
No, I understand this slide. I'm just saying the relation to the previous slide.
Yeah.
Is basically this is the total number of things that you have to compute when you pick the set T. So the total things that you have to check when you pick set T is basically d to the power n minus k.
Yeah.
And then you have k, m choose k possibility for picking set T.
I'm not sure. I'm not really sure where you're headed with this, but let me admit this. This is not exactly. This is not the only thing that you need to get a lower bound on R, because while this says that this is the best way to pick a single reducer,
Yes.
and the method I gave does pick the single reducers, there's still this other added question of what's the best covering, what the covering number is, and therefore what sets of dimensions should I actually pick.
It says what's the maximum number of outputs that
one reducer can get. So what I'm saying is we're getting as many outputs as we can from one reducer by the algorithm that I described. But what it doesn't say is that, given that usually the lower bound on covering number can't be met,
I see.
it says that there might still be something a little bit better. But at least if you're gonna worry about the question of what what should you do with one reducer of size q? It says this is the best thing you can do with one reducer of size q, is what I suggested. Okay, now let's say I want to just finish up just very briefly talking about two extensions. Okay, as I said, I've made this assumption all along that says that the side of the cube is the same in each dimension. It's not really. On the other hand, you can get a you could think about a more general problem in which you talk about a weighted covering, where the dimensions have weight, which is probably the log of their actual extent. And I'm going to allow the sets that I use, the sets S that I use for covering, to have different numbers of dimensions as long as the sum of the weights of those dimensions is up to some limit. Okay. In the paper we actually talk about, just give a simple example where you change, you group the dimensions by their extents. There's the little dimensions, the middle extents, and the big extents, and you handle each of those three groups differently. Again, obviously don't have time to really talk about this in a lot of detail, but I want to just again introduce another fairly interesting combinatorial problem in which the idea that we're going to compute all kth order marginals, let's say k equals 3, from scratch, not very likely. Okay. More likely you're going to compute the first order marginals from scratch, and then you compute the second order marginals from the first order marginals and the third order marginals from the second order marginals, and so on. And this presents a similar but yet different problem. And here, what we really want to do, if I want to compute, if I want to compute kth order marginals from say jth order marginals, where j is something smaller, then what I'm really, and I want to use let's say reducers of size d to the m, or again, since d may not be a constant, but something exponential in m. Then what I want to do is I want to cover sets of all sets of size k with a pair of sets s and t, where you cover a set if the set u, if t is contained in u, and u in turn is contained in S union t. So the things you can cover, the u's you can cover are t union k minus j members of the set S. Okay, so again, so the algorithm that corresponds to this to this covering problem is we'll assume again reducers of size d to the m, and it's going to get all the jth order marginals that aggregate over the j dimensions in t, and have fixed values for all the dimensions except those that are in S and T. S and T might as well be this joint. Okay, so I can define, again, just like the covering number problem, I can define another covering problem. D of nmjk is the number of pairs st that I need, where S is of size m and T is of size j, and every set of size k out of n dimensions is covered by some pair in the sense that I have on this slide. Well, let's see. You can get a lower bound. Again, it's similar to the covering numbers. It's again, you have to cover n choose k sets, and the number of sets that would be covered by any pair is m choose j minus k. I mentioned we've been sort of working on this recently, and one interesting result is that you can actually reach the lower bound for for d of n212, which is computing second order marginals from first order marginals using a quadratically sized reducers. And even that looks kind of tricky. I think we also have a way to express these in terms of a sum of C's, but I'm really not ready to talk about that. Okay, so I want to close with just some open questions. Okay, so the first thing is when I don't fix the dimensions, assuming that the dimensions vary in an extent as they really do, I want to get I still want to get an upper bound on how many hypercubes of dimension k you can cover with with q points. And the trouble there is the way to get the most hypercubes is to concentrate on the little dimensions. But that's not adequate because you do have to cover all the dimensions, including the big ones. So, just how do you even get an upper bound? Sort of what is the optimal way to given a fixed reducer size to break up, to assign jobs to or sets of inputs to the reducers? That looks like a very hard open question. And so probably more tractable is this weighting, the sort of weighted covering number problem that I alluded to a while ago. Again, as far as I know, there's really nothing known about this covering sets by pairs problem that I talked about just a moment ago. Again, another interesting question is this Hamming. Again, we have optimal algorithms for Hamming distance 1. We do not have optimal algorithms for even Hamming distance 2. And moreover, it's not even obvious what the actual relationship between R and Q should be. And then, ideally, is this generalizable to more than 2 ranks? Or even, are there other problems like matrix multiplication where you can at least say 2 ranks, but 2 stages or 3 ranks are better than 2? Okay, I don't know. Okay, so with that, I will.
There are a number of questions already, but is there any other questions? Yuri?
I'm not sure I got everything right, but this marginals code in mind distributions. So in addition to upper bounds, lower bounds, one can try to compute expected values for sort of average data. That doesn't make any sense, does it?
Well, why isn't that just an nth order marginal? As the average is where you sum over everything. And then I guess divide the point.
Can you repeat?
I'm saying if all you want is the average, then you just sum over all the points and divide by the number of points.
So the average is easily computed, you say?
Yeah, easier, yeah.
But it may be useful.
It may.
I mean, it's just one output, right? So it doesn't fit into this framework.
Well, no. It's a fairly simple input-output mapping where all the inputs
Map to one output.
map to one output. Now, if you want, sort of average of averages of subsets of marginals, yeah, then things get complicated again.
Have you thought about problems where there's more skew? I'm coming at this kind of from a natural language point, where words in the English language, the will have a very high count, whereas the common nouns will have a much lower count. So you're going to have this skew. If you have some problem where I need to pair of with all of the words that can follow of, and I try to send all of those pairs of cat, of dog to the same reducer.
Actually, there was a student at Ben Gurion University who I wound up sort of coaching as sort of informal advisor, and that was sort of what he was doing weighted all pairs. In fact, making you don't even have to talk about the and of. It's you know, the drug records, they're not really all the same length. They're, you know, proportional to the use of the frequency with which the drug is used, and those vary widely.
And do we have results on how we should cover these with reducers?
Well, he had some results in his thesis, yeah.
And one follow-up, if I could. If you thought about combiners, so in practice, when we have...
I mean, I know what they are.
Yeah.
I try to ignore them because it just messes up the theory. Especially the matrix multiplication theory. The others doesn't, but for matrix multiplication, it does.
Can I ask what was the first open problem again, the one with non-fixed dimension extent? I just didn't understand. Covering the hypercube.
Yeah. Now here's a place where you probably need to talk about averages, because again, what you want to do is you're not just going to ask the question, what's the maximum number of hypercubes I can cover with Q points?
Okay.
Because again, the answer, you know, if I have some very small dimensions, that answer will be a lot. Okay, but what you want to say is if I'm given many sets of size Q, and I need to cover all the hypercubes of let's say K dimensions, what's the best way to you know, how is the best way? What's the best way to pack them so that all of the hypercubes are covered by some you know, by some set of Q inputs. It's really just the problem. It's just really the question of what's the lower bound on number of reducers needed, you know, when the dimensions are varying extents.
So it's not a question about one reducer, right? Like you want to.
Well, yeah. See, I'd like it to be a question about one set of size Q and how many can you cover. But the fact is, you can cover many. You know, if you use the small extent dimensions, you can cover lots of them.
Yeah.
But if you use the big extent dimensions, you can cover very few of them. You want to sort of get an average. Or a better way might be to say, I'm going to charge you more for using a small dimension.
Yeah. Okay.
Okay. And then if I got the right function.
And then you can define the problem for one reducer.
Yeah. If I got the right cost function, then I could say, you know, so that it didn't really matter whether I was picking small dimensions or big dimensions.
Yeah.
Then I might get something there. But the goal, of course, is really just to answer the question: how many reducers do I need to cover all of the subcubes of a data cube that has dimensions d1, d2, and dn. David,
I was hoping you might tell us which drug combinations to avoid.
Well, it's in the literature, and incidentally, they did find 40 of the 80 known drug combinations. And they also found 2 others that were not known. And I've told them that you got to go to a physician and find out, are these real? again, because they were only looking at 3,000 of the 6,000 possible drugs, I'm not surprising that they didn't find them all. But it looked, that's a pretty good a good number. I never did find out whether what the other things they discovered, whether these were simply statistical anomalies or were real, or maybe were real but had a simple explanation. Like before they started normalizing for ages of patients, they had discovered things like acne medication cures heart attacks. Think about it, and you have to be a little bit careful. If you're not a physician, if you don't really understand the drug, you can't be sure that the data, the results are good.
So when you were thinking about matrix multiplication, it was in the traditional way of multiplying a row by a column. So what about some algorithms like Strass's algorithm, where the complexity is lower, or does that even fit into the MapReduce kind of framework?
Well. Remember, for us, an algorithm has to be done in two ranks. So Strass's algorithm is recursive, can't be done. I mean, all we could do would be to look at one stage of Strass's algorithm. That would give us, there would be some other mapping schema. We did not try to look at that. You probably wouldn't get anywhere. But you could think about that if you wanted to. It'd be interesting to see if you could get something.
Other questions? Thanks, Jeff.
Okay. Thank you.